I think we solved this problem already, right? So we'll go through the next slide. Next slide, it's a, continuum concept of fluid. What is the continuum concept? It meaning that there is no empty space or void within the fluid. That is called continuum concept of fluid. For example, if you right now sitting in a room, you make the door and window conceal, then you take out all the air and you put say 1 liter, 1000 cc of air or 500 cc of air. The molecule of the air uh, will move from each other. That means distance from the molecule will be increased, but they will fill up every corner of the room, and we will think that there is no empty space or void within the fluid. That concept is called continuum concept of fluid. So why we consider that? There might be sometime you look in the river, in the pond, you see bubble are getting out. Why? Because inside there is some air. But for mathematical purpose, to derive a formula or equation, we need to think there is no empty space. If there is empty space or void, then you need to consider two things, that liquid fuel and also a mixture of some gas or bubble or air bubble, right? So for simplification, we'll think that there is no empty space or void within the fluid. So it's saying mathematical idealization of fluid as a continuous distribution of matter. That means continuously it is distributed. There is no discontinuity. It's a with no empty space or void. As most engineering problem, fluid have large size of molecule. There will be size molecule and distance between molecules are very small. That we are assumption when we derive the fluid equation or formula. As a consequence of the continuum assumption, each fluid property is assumed to have definite value at every point in the space. Thus, fluid properties such as density, temperature, velocity, so on are considered to be continuous function of space and time. So what does it mean? For example, you are sitting in the room and it is a rectangular size room, your room, right? So you take out all the air, or say you have the air in the room, your window is open. So the density and temperature of your room is not the same in each corner. For example, if I think this is the roof of your room, right over, okay. So you might sitting somewhere. So for example, you are right over here. So this location, you will have one temperature. Then some location you might have a computer, you might have a light bulb, or you might have a fan running. So over here will be different. Even we are saying that in the room have a very little fluid, that you seal all the window and door, take it out, and you put 50 cc of oxygen, then it will occupy the every space of the fluid. But still it will have the fluid particle will have density, will have temperature, and will have pressure. That is saying the fluid property should have a definite value. That means fluid property value is not the non-zero. And in every space, why they are saying about the space, because if you think about the room, if you think this is x-axis, vertical z-axis, along this direction, y-axis, then if right now you are not opening your window, but you are running fan, so your density of the fluid or air and also temperature, might be pressure too, will vary from one place to another. That means it will not be the same. Then you open the window or of keeping open the door, then what will happen? Air will enter through the window and might be get out from the door, or vice versa. In that case, the air coming or getting out through the window is not the same every time, because air velocity is changing respect to time. So density, pressure and temperature of the air inside the room also depends on the time. So we are saying that all the fluid property, we are saying fluid property is function of space and also time. So what does mean space and time? Space means you identify a point in a location. If it is in the floor, you can just give two x and y coordinate. But say it is a point just close to your fan, ceiling fan, then you need 3 coordinate, right? So that's why it's saying that fluid property is function of 3 value. What the function? Function of x, y, z, and the t. Okay. So right here it's saying, as a consequence of continuum assumption, is fluid property is assumed to have definite value. That means property is not zero. You cannot say that density is 0 or temperature is 0. No, it has a certain value. Thus, it's saying over here, thus fluid properties has as density, temperature, velocity, and whatever other property like entropy are considered to be continuous function of position and time. Density at a point may also vary with time as a result of work done or by fluid or heat transfer to the fluid. Thus, complete representation of density in a fluid field will be given by rho equal to function of x, y, z, and t. For example, right now you might join with the laptop or cell phone. After 5 minutes, you also turn on a desktop. So in the desktop, your CPU getting heat, releasing heat to your room, right? So your temperature density will be sensed. That means it depends on the time too. Okay. So from this slide, you just remember that fluid we are considered there is no empty space or void in the fluid, and fluid property must have definite value, and their function of or they depend on the 3 coordinate x, y, and z, and also time t. Okay. Now, continuum concept of fluid, based on this concept, there might be 2 type of fluid, like in viscid, that means fluid don't have viscosity. Then viscous fluid have viscosity, that is laminar and turbulent. Then you have internal flow and external flow. And in viscid, then you have incompressible and compressible. Incompressible means fluid is not compressible. And internal and external flow fluid. For example, natural gas flowing inside a pipe, that is the internal flow. And what is the external flow? Water running through a river, that is external flow. Okay. Next topics, actually these topics sometime also needed in that to study the thermodynamics. I think, do you have thermodynamics class in 2.2 or 3.1?
So we have one course in 2.1, sir.
On 2.1 thermodynamics. Okay. So I feel you already know the system, control volume, and control surface. It's a system is defined as a fixed identifiable. That means you can identify. You cannot say is volume 0 or mass 0. So it's defined as a fixed identifiable quantity of fluid, some amount of fluid. The system boundary separate the system from the surrounding. That is called the system and the boundary. The boundary of the system might be fixed or movable. However, no mass crosses the system boundary. You are sitting in the room, you close the window, close the your door, that means the whole room is a system and wall of the room is the system boundary, because wall separate the all the fluid inside the room from the outside. Similarly, you fill up the your gas tank for your car, then the wall of the cylinder is the system boundary, because it separates the inside methane gas from the outside air. Okay. Then control volume. Control volume is an arbitrary volume in space through which fluid flow. That is called control volume. Like giving an example over here, like a T joint, fluid coming from this end, then leaving through this end. So this portion of fluid, you can think this is a control volume. For example, your pipe flow, fluid passing through the pipe flow. So if I take a segment of the pipe, like this segment, actually what will look like this segment? Like a coin, right? It will be like a coin with certain thickness. It will have some thickness too, right? So this is a control volume, is imaginary, and through which fluid is flowing along this direction and getting out from this direction, right over here. Okay. So what is the use of control volume and what is the size of the control volume? It depends on what you are deriving. You deriving equation, what type of equation, what is the what type of flow and what type of liquid. So just remember that sometime to derive equation we assume there is a control volume. Then control surface. Control surface, that means the geometric boundary of the control volume is called control surface. Control surface may be real or may be imaginary, and it may be at rest or in motion. Uh, your system boundary might be fixed or might be movable. Anyone can give a system boundary with movable, that your boundary is changing. For give example, I give example of gas in methane gas, that is a fixed system. System boundary is not changing. But if you think about a piston inside a cylinder of IC engine, then you see system boundary is moving, because control volume also changing, right? Because piston is moving back and or up and down or left, right, right? Okay. Okay, next thing we need to know what is fluid particle. And fluid particle, we know there is a fluid molecule. We're not talking about the molecular level. We are talking about a fluid particle. So what is the fluid particle? And what is the application? Again, to derive the fundamental equation of fluid mechanics, sometimes we think a um, lump of fluid. Lump mean some quantity of fluid, and we'll think that it has a certain shape. It might be a circular disc, might be a triangular, or might be a cube. Okay, but it has a dimension. Whatever small amount you think size, it has a definite shape and definitely it has some dimension, and also it have mass and it has density. It must have all the fluid property, because we already told you that there is fluid should have a finite value of property. Okay, so fluid particle, an infinite small lump of fluid is called a fluid element or fluid particle. A fluid particle assumed to have very small but non-zero dimension. That means dimension you cannot say non-zero, must have non-zero. Its volume you can say delta V, that means very small volume, very small mass, it has a density, and also it has a pressure temperature. And if your mass is delta M and volume is delta V, then delta M by delta V equal to rho. And what will be the shape of the fluid particle? The shape of the fluid particle may be triangular, may be prism, cylindrical, or spherical, depend on the type of the fluid, what coordinate system you are using, and what type of fluid. Okay. So this was from lecture sheet 1. Um, any question? Anyone has any question from lecture sheet 1? No? Okay, so we'll stop lecture sheet 1, then we'll start lecture sheet 2. Okay. Uh, could you hold on just okay. So this chapter or lecture is include static pressure. So what is the static pressure? Static mean nothing is moving, right? That is called static body. So static pressure mean if a fluid is not moving, then how much, what will be the pressure you will get from the fluid, that is called static pressure. For example, just a while ago, I took the tea. So this is my cup, right? This is my cup and fill up with tea or coffee. So in that fluid is not moving, but all the surface of the cup experience pressure, and pressure always work perpendicular to the surface. It don't matter what type of fluid inside the container. Okay, so this pressure is static pressure. So the chapter name is static pressure. And if fluid start to move, then it will be different than static pressure. So let's see what we have in this chapter. In the fluid mechanics, it's a mechanics. So I'll explain you, coming from the engineering mechanics. That engineering mechanics we apply in the fluid mechanics. That is the basic difference from the engineering mechanics to fluid mechanics. But all the equation law you have to use in the fluid mechanics from the engineering mechanics. So we will use sometime this equilibrium of static body equation, the summation of fx, fy, fz equal to 0. And also sometime we use summation of moment, all three axes is equal to 0. Then for dynamic body, that means fluid is moving or a moving object. How a moving object move? Obviously, some force working on that body. In that case, summation of fx along will be equal to m into ax. That means summation of force working along y-axis equal to mass into acceleration along y-axis. Similarly, right over here. And other thing I mentioned over here, if we have a force, this force F, you can divide into component. One is Fx, other one is Fy. Fx will be this mass, F cos theta, Fy, F sin theta. That sometime we need it. So I put in the slide, just refresh your mind. Okay. Then write over here the vector quantity. Okay, yeah, these two vector. One vector is A, other one is B. So how you can figure out the cross product of two vector and dot product of two vector. So this is the cross product, this is the dot product. And cross product also you can figure out by matrix, 3D matrix, right? And right over here is the del operator. You see, you learn from the your math course. And this del operator is a vector quantity and we will use in the fluid mechanics sometimes, okay? And how it is used, like del S, you will have S over here. If you use like del U, if I say or del U, then in every where there will be U with the del operator, okay? And you have a vector V, and this vector, if you make dot product with the del, then result will be this one. That mean for dot product, there will be scalar rashi, okay? Scalar vector, no a vector quantity. So this one will multiply with the U, and the y component will multiply with this y velocity v, and this one z component will multiply by the w. And if you make cross product, then you can use the matrix, okay? But you don't be scared that you already study math, why we need to study again in the fluid mechanics. We will not derive everything, but when you derive the formula, sometimes we need those equation or those operator. That's why you put it over here, okay? Again, if a function is P or pressure, it depends on two quantity x and y, how we can figure out the change of pressure. So then change of pressure will be dP by dx into dx and dP by dy into dy, okay? Just remember. Then I put some derivative, and you already know it. Just look in the this slide when I give you the PDF file, so you can refresh your mind, okay? Now, we need to know two things, that what is normal stress, what is shear stress, what is the deformation rate of the fluid. The normal stress always work perpendicular to the surface. And now how we'll figure out the normal stress? This normal stress, sigma equal to, I put P over here, right? That mean is the force, P is the force, not the pressure. So I say sigma equal to F divided by area, okay? And it will be same unit of the pressure. But if you consider that how much will be a stress in a bottom of bucket if filled with water. Say you have a bucket full with water, and you like to figure out how much will be stress or pressure at the bottom of the bucket right over here. So you can easily figure out. You figure out the weight of the water. So how to figure out the weight of the water? You need to figure out the volume of the bucket, then multiply by density. So if you figure out the weight equal to volume, then you multiply by density. How do you present density? By rho, right? So V rho, you will get the weight of the fluid. So this weight of the fluid will come, unit will be Newton. And this working where? Just the small area of the bottom. What type of area in the bottom? It is circular, right? If you have diameter of the bucket, you can figure out the area. So your stress sigma will be force by area. What is the force now? That means W, weight of the water. You divide by area, you get the stress. Okay. So just remember, stress always work perpendicular to the surface or perpendicular to the cross section. So other thing that if I took a pen, then I'm pulling that pen. That means I apply tensile load, right? So that load or force will be perpendicular to the cross section. I'm trying to pulling along this direction, pulling along this direction. So cross section, this pen is circular. That means this stress, how much will be stress in that case? Normal stress. Normal stress will be force by area. So if you know the force, say 20 Newton, divided by the area equal to pi r square, you will get the normal stress. And this stress, you see, stress equal to force by area. So stress equal to force by area. Force is a vector quantity. So stress also a vector quantity, it has a direction. So in that case, how the stress working? Stress is direction is perpendicular to the surface. That's why it is called normal stress. And what is shear stress? Say this is the pen. If we like to do like that, that means I applying force parallel to the cross section. That force will create shear force in the pen. And if you divide by the shear force by the cross section area, then you will get the shear stress. So shear stress will try to divide the parts into two parts. Okay, shear force. So shear force always work parallel to the cross section. What here is saying shear stress work parallel to the surface or parallel to the cross section. How will figure out the shear stress? Tau equal to shear force divided by the area. And you learn more in your solid mechanics class about normal stress and the shear stress. For example, you have bucket of water and you start to move your hand, do like that, put your hand like that in a river or pond, you try to moving your hand like that. That means you applying some shear force in the fluid, okay, because it is parallel to the surface. Other thing we need to know, deformation rate. Rate of change in distance between two neighboring points moving with fluid divided by the distance between the point, that is called change in length per unit time, that is the deformation rate. For example, if I say a rectangular fluid element right over here, and its length is L. I'm saying rectangular fluid element. That means it is actually 2D, it is a rectangular, but in 3D, it is a kind of cube, right? It will be a fluid element like that. So this fluid element, when try to move within the fluid, then its dimension might be changed. How? Say if I look at the 2D, this is this is, and this one coming might be like that. That means shape of the fluid element is changed. This change might become due to the shear force you applying by your hand or due to the other reason, turbulence or other reason. So initial length of this one was how much? Was L, right? So initially L, right now it is, this length is not the L. If I say this length is LF. final length, and initial length was Li. So what is delta L then? That means change of length, delta L equal to final length LF minus Li. So what is the change of length respect to initial length? We can easily figure out, right? Then your change of length is del L. Del L. Then this del L is divided by the initial length. That means you are getting how much percent in terms of or ratio the dimension is changing. So you divide by Li. Now this to changing the dimension, it takes some time. Might be 1 second or millisecond. Then you divide it by the time t. That is called deformation rate. That a dimension is changing in respect to time. But what is the rate? Similarly, I just showing a linear distance is changing. Similarly, volume might be changing. You can figure out rate of change of volume. How? Your change of volume will be del V. If I write there, change of volume will be del V. This del V you divided by the initial volume. Then how long take time to change this volume? Say 2 seconds, 3 seconds or millisecond. So it divided by whole term. If I put in the bracket, then this whole term is divided by your time. That is small time is del t. Then this will call the deformation rate of volume. Okay. And in this case, right over here, for example, you need to know other thing, what is shear strain or angular deformation of the fluid. If you think initially a fluid element is rectangular fluid element, in this rectangular fluid element, then you apply some force or removing by your hand due to the hand, this end coming right over here and this end moving right over here. So how much is change? Your change in length is x. The height remains the same. Now, I like to figure out that what is the angular deformation, how much angle it is changing. If it travel faster, then this angle value will increase. So you apply tan gamma right over here. Yeah, if I apply tan gamma, then what will the value? Perpendicular by base, right? So my perpendicular distance is the x. What is the base for this in terms of this triangle? So it will be x by L. L is the height of the element. So it will be x by L. But if angle is very small, then tan theta equal to theta. So I can say only gamma equal to x by L. Okay, that is called angular deformation of the fluid. And for this deformation, say you putting hand in the bucket of water, you do like that for a while, you take out your hand, you will see still fluid is rotating. That continuously, if you think there is all the fluid element is rectangular, they having the deformation. That means initially they might be a shape like a brick, but after a millisecond, the its shape is changing. Okay. Any question so far? Okay, now we'll derive a equation which is called Newton law of viscosity. How it look like Newton law of viscosity? The Newton, he derived this equation and he figured out by experimentally from his experiment. So what he did, he take a plate, a rectangular plate, and he keep that plate on a table, and this plate is fixed. Fixed mean this plate is not moving, is not moving. Then he put another plate in some distance, say they have some distance between them, and inside between these two plates he put some fluid, and he tried to move this plate with certain velocity. So what does it mean? Obviously, due to there is a fixed plate, then top of the fixed plate you have some fluid, then you try to move the one plate with certain velocity. So obviously you need some force. Without force, the plate will not move. If you like to move faster, you need more force, right? Then if you need to move with a bigger plate, then you need higher force. So bigger plate mean the area of the plate, the upper plate is increasing, right? If area increase, you need the bigger force. And also the amount of force you need to move the plate will depend on what type of fluid inside. And it is a water, or it is just vegetable oil, or like a tar or honey. If it is a denser fluid, then you see you might need the higher force. Other example, say you have a boat. You have a boat in the river, and bottom of the river is this much height. That means bottom of the river are kind of fixed plate. And if you think the bottom of the boat, how look like? Kind of a flat plate, right? So you have a certain distance, say 2 feet or 12 inches, whatever the distance. You can easily able to move the boat. But obviously, you need more force, right? But say water height is gradually decreasing and is coming this much level. Say just say 3 millimeter or 4 millimeter water. Then you try to move. Do you need higher force or less force? If water height decrease, anyone?
Higher force.
Obviously, you need higher force. Why? Because the density of the water is changing. Because at the bottom there will be some clay, so water property is changed. So you need to apply higher force to move the boat. And if boat is bigger size, you need to apply higher force. You like to move faster, then you need higher force. So you see the force, it depends on some value. One thing, it depends on the amount of force you need to move the plate is proportional to the velocity u. Because u increase, you need higher force. You like to move slowly, you need lower force. Other thing, the size of the plate. If size of the plate is too big, obviously you need higher force. So F is proportional to area. This is one thing. Other thing, if the height decrease, you need to apply more force. Height increase, you need to apply less force. That means F is inversely proportional to the height of water. In that case, it will be Y. So I can say F inversely proportional to the height of water. That means Y. Okay. So you see what Newton did, he keep bottom plate rest is stationary, U is 0. Then upper plate he tried to move with force F and velocity U. And height between this plate is Y, and these two plate, the gap is filled up with some kind of fluid. Then he take the different plate, different height, different fluid and try to figure out the characteristic of this force. So you see, we found these three variation of force. That force depend on these three parameters. So this one I can express in one equation. I can say F equal to AU. I'm sorry, not equal to, proportional to AU divided by Y. I can say, right? And from here, I can simplify more. I can say this A, I like to bring bottom of F. So I can say F by A proportional to this U divided by Y. I can say bigger Y, okay, not the smaller Y, okay. Now, this U by Y, I like to express in other term. What is the other term? U, bigger U divided by bigger Y. I like to put in terms of du divided by dy. So du by dy, what is that one actually? Change of velocity respect to y, du by dy. So this term is called velocity gradient, but I need to justify that how I can write bigger u, that mean velocity of the upper plate, and bigger y, that mean distance between two plates, and this term is the rate of change of velocity along y-axis, right? But how I can do it? If you, let me erase all those things. If you look to the figure, and also we already told you before, the fluid particle or fluid flow layer by layer, one layer over the other layer. So bottom plate is fixed. So fluid particle try to move, right? This plate, right over here, one more plate. So I'm saying it flowing in a layer, say one layer by layer, and this is our upper plate. Upper plate is moving with certain velocity and force. So what will happen? The fluid particle right this location, thus bottom of the upper plate. This plate is moving with velocity u. So what will be the velocity of this fluid particle? Same as u, because he like to stick with the upper plate due to adhesion property. Okay. Similarly, the bottom plate is not moving because it's stationary, u equal to 0. So what will be velocity? A fluid molecule or element just close to the bottom plate, 0, he will not move, right? Now this fluid particle moving with velocity u, what will the fluid particle write this on? What he will do, you have fluid particle right over here, right? He will try to move with same velocity of this one, upper one. But this element or this layer will hold him. He'll say, hey guy, don't travel faster. He'll offer resistance, okay, resistance to flow. So he will say with time delta t, this fluid particle will come right over here with velocity u. But this one, he like to travel by same distance, but he cannot because bottom layer try to hold him. So he will travel little bit less distance right over here. Similarly, this one will travel right over here, and bottom one will be at the rest. So if you make the distribution of velocity, then it will be kind of triangular form. Okay. So if you look right over here, I am say this plate is not moving. So all the, if I took some fluid element right over here, or I'm saying right over here in different level, I have a bunch of fluid element. So bottom fluid element, he will not move. He will stick with this plate. And upper fluid element, he will stick with the bottom surface of the upper plate, and he will travel faster with the plate. So he came in right over here. In the bottom one, he will not travel with the same speed of the upper one, because this one tried to hold him. So he came in right over here. Similarly, all the fluid particle coming over here. So the velocity of the fluid particle is changing along y-axis. So from that relationship, we need to figure out that we can write down bigger u by y equal to del u by del y. So how we can write down? You see, if I take two fluid element, this fluid element and this fluid element. So how much distance they travel? The difference of distance is, see, if I make a line over here, then it becoming a triangle, right over a small triangle. And this distance from here to here will be how much? Change of velocity, right? Del u. So I can say this is del u. And this vertical height between this point and this point, I can say del y. Now you see this bigger triangle and the smaller triangle is similar. So we can use the similarity of the triangle. So for bigger triangle, horizontal distance is u and vertical distance is y. So uy equal to, what is the horizontal distance in the smaller triangle? du, and bigger, and the vertical distance dy. So you see, bigger u by y equal to du by dy. Then we can write down over here. Okay. And other thing, F by A. F by A mean shear force. You see over here, all the force working parallel to the surface of the plate. So this force is called shear force. So tau equal to F by A. So right over here, what we can write down? We can write that F by A, proportional to, say PROP, proportional to bigger u by bigger y, or we can say, or du by dy. Okay. Then in the next line, what we'll do? We'll take out the proportionality constant. Then see, we'll get a constant. And from that constant, we'll get a fluid property. You see right over here. So what we did, F by A equal to tau. Okay. So left hand this equation, we can say tau. And du by dy, this one equal to bigger this one. Okay. And if you remove this proportionality constant, then we got this equation. Tau equal to mu du by dy. That means mu is the proportional constant. So if you look carefully, what we are getting actually, tau equal to how much? A by A equal to mu. I am putting mu, that means some constant, times du by dy, or you can say mu star del u divided by del y. Now, if mu increase, then what will happen? If mu increase, you need more force, right? That means the mu is the fluid property. If a fluid has a higher mu, you need higher force. If fluid has a lower value of mu, you need lower force. That means force to move the plate, it depends on a property of the fluid that is called viscosity of the fluid. Okay. So let's look through the next slide. The equation we found right over here. This equation is called Newton law of viscosity, this one. So right over here, the equation tau equal to mu du by dy is called Newton law of viscosity. And mu is called proportionality constant or coefficient of viscosity. Sometimes it is called absolute viscosity. Absolute viscosity, sometimes also called it is dynamic viscosity or just simply viscosity of the fluid. And this term du by dy is known as shear strain, shear rate, or sometimes it is called velocity gradient. You already now know this name from the mathematics class, vector gradient or velocity gradient. Velocity gradient means change of velocity, rate of change of velocity in a certain direction, or also it is called shear deformation. And unit of this mu is Newton second meter square, or sometimes it is expressed by poise. So what is the poise? 1 Newton second meter square equal to 10 poise. And this mu, you divide by the rho, you will get the kinematic viscosity. Okay. Our class will be finished at 10:30. Right now we have 9:40. Do 14 about 9:50, I think. Do you want some break? 2-3 minutes? Hello? No? Okay.
No, sir.
So we can go through the next slide. Okay. And we'll write over here, we'll use the Newton law of viscosity to solve a problem. Let's see how we can solve it. It's saying a plate 0.0254 millimeter distance from a fixed plate. That means you have a fixed plate right over here, then you have another plate. And distance between these two plates is 0.0254. That means this is given y, bigger y, right? Moves at 61 centimeter per second. The upper plate is moving with certain velocity u. So you see u is given over here and y is given. So y is given, you convert in millimeter, and u is given in centimeter per second, you convert in meter per second. Now force is given, it's a require a force of 0.2 kg force meter square to maintain this speed, and find the dynamic viscosity of the fluid between the plate. So is maintain this velocity force, this amount of force you needed. What is the unit of the force? Unit of the force is Newton. But they are not giving direct force. They are saying force kg per meter square. The kg is not the unit of the force. So how will you get the force then? If you multiply by g, that means 9.81 kg per meter square, then you will get the some number, and your unit will be Newton per meter square. That means that is force. So right over here, 0.2 kg force per meter square, actually it is giving force per unit area. And force per unit area, it actually equal to the tau, because tau equal to force F by A. So tau is given. So what we did is that tau equal to the force per unit area, given force per unit area. So you multiply by 8.91. So your unit will be Newton meter per second square. So this is your formula, du by dy, and du by dy equal to how much? Capital U by bigger Y. So capital U is given 61 centimeter per second. Distance to plate already given. So we have this value. From there, tau value is right over here. So you figure out the value of mu. Okay. And what is the, in real life, what is the application this problem? Sometime you will see in CNC machine or in the lathe machine or shaper machine, you see the table of the machine is moving with certain velocity, and he is moving over a fixed plate, and you see they are using some lubricating oil. So you need to figure out that what type of oil you need to use, what will be the viscosity of the oil to move a plate with certain velocity. Okay, this is the application. And other thing, for example, if anyone know the journal bearing, say you have a ring. Okay, it's obviously it has a certain thickness, right? And inside this ring there is a shaft, and this shaft is rotating inside, and there is nothing, is not supporting by bearing, but it has only fluid. And when this shaft is rotating at a certain velocity, rotational speed, then fluid also rotating, and due to the uh, layer of the fluid or the film thickness, it has a certain thickness. How much thickness? Distance from here to here. This shaft is not touching the surface of the ring or bearing. Okay, so if this shaft is rotating, that means shaft is supported by some fluid. So here is the also application, that what type of fluid you needed to run this shaft, to rotate this shaft with a certain velocity. For example, you are working in a manufacturing company, they make the journal bearing. This type of bearing is called journal bearing. So you need to figure out what happen if you use too denser fluid, then you need higher torque to rotate this shaft. So you need to make sure that you are using the right amount of right type of fluid. For example, if you have a car or truck, you have differential gear in the rear axle. They have a specific fluid. If you use the higher fluid, higher denser fluid, then what will be happen? Your bearing will be damaged. Same thing, engine oil. They have a manufacturer has a recommendation that if this is the specification of the engine oil you use in your bike or you use in your automobile engine. But if you use the wrong fuel, if you use too fluid has very high viscosity, then what will happen? Then rotating parts will not try to move perfectly because you need higher force to rotate the parts. Again, if fluid is, say, density is very low or viscosity is very low, then what will happen? Fluid will not stick between the two surfaces. Then this shaft will ultimately, during rotation, he will touch this bottom surface and it will damage your shaft and damage your ring or bearing. Okay. So there is a application of this Newton law of viscosity, and we will solve there is one more problem right over here. Then you realize that what is the application of this equation, Newton law of viscosity. So what is that equation? We know that tau, if I write down with the mouse, that tau equal to mu du by dy. Or you can simplify. Instead of a tau, you can write down f by a. F by a equal to mu. Instead of velocity gradient, you can say velocity of top upper plate divided by the distance between them. So this equation, you need to apply to solve some problem. So right over here is a problem related to the journal bearing. You see it's saying a cylindrical shaft of diameter 95 millimeter. So a shaft has 95 millimeter diameter, rotate at a speed 50 RPM. So he is rotating at a certain RPM. That means N is given. N equal to RPM equal to 50 revolution per minute, right? So what is the angular speed? You can easily figure out from the RPM. So angular speed omega, it will be 2 pi n divided by 60, right? And what will be unit? Radian per second. So I'm just saying R per second, radian per second. This is the angular speed. So if I think that a point in a shaft, what will be his linear speed? Anyone? What will be the linear speed, tangential speed?
Equal to omega r.
Good. V equal to omega r. You see, so easily you can figure out this U. Okay. So it's saying this shaft is rotating inside a cylinder of 96.5 millimeter diameter. You see, shaft diameter is 95, but the cylinder diameter is 96.4. That means he is bigger than the shaft, right? So I am saying this is the cylinder. And cylinder is not moving, only shaft is moving. It's a both shaft and cylinder has certain length. What is the length? 50 millimeter long. If the torque required to rotate, okay, this shaft will not rotate automatically. You need to apply some force or torque, right? To rotate the shaft, you need to apply torque T. T equal to given 1 Newton meter. 1 Newton meter torque you apply, then is rotate with 50 RPM. Now it's saying find the viscosity of the oil occupying between the shaft and cylinder. What type of fluid you need? What will be the viscosity of the fluid? That you need to figure out. So very practical example of application of fluid law to design something. Okay. So you see, you look in the formula, this value they like to know. What will be the value of mu? And what you need to know, you immediately, after you read the problem, then immediately you have to realize that I need to use this formula. Since it is a say find the viscosity of the oil, and a shaft is rotating inside a cylinder, there is a gap between, and they're saying in between they have a fluid. Obviously, it is similar to the same problem, that a plate moving over another plate. So you immediately realize from your brain that you need to use this equation. Then you simplified form, tau equal to F by A, and del U by del Y equal to bigger U by bigger Y. Now, you see value of Y, gap between the two shaft and cylinder, you can easily figure out. Because 90 from here to here, diameter is 96.4. And from here to here is 95. So you just figure out both radius, difference in radius will be value of Y. So you see Y value we know. How will get the value of U? Right over here. You figure out the N is given, RPM given. You figure out angular velocity, then angular velocity multiplied by the radius, you get velocity U. Now, area of the plate, how will get the area of the plate? And how will get the force? You see how this shaft is rotating. If I draw right over here, you apply torque, right? Torque T. So I can say,
There are two diameters.
what to say?
So there are two diameters. So which one will be the R, the smaller R?
There is a radius of the shaft you can figure out 95 by 2, right? Then you figure out radius of the cylinder 96.4 divided by 2. Then you subtract, you'll get this space. Okay, we'll show you. I just giving you the fundamental idea that how we can solve this problem. Okay, now you need to figure out the force and area. How will get the force and area? At first, you look to how will get the force. You applying torque, shaft is rotating. So instead of torque, that what does it mean? That means you applying a force F tangentially. You apply force right over here tangentially. Apply force over here tangentially. Then you have the torque. That means this torque T equal to F into R. I'm saying this torque equal to F into R. So you see torque is given 1 Newton meter. Radius of shaft given. So easily you can figure out the F. Now, how will figure out the area? Actually, what happening? This is the shaft, right? So it is rotating. What does it mean? If I cut it and pull, that means a plate at certain, we say this is the plate. If I make it round, it become shaft. It is rotating. That means this much distance actually moving. So what is this length? 2 pi r, peripheral distance. And what is the length of this S, L of the shaft? So area will be L into 2 pi r. This is the L, this is the 2 pi r. Same thing, your car wheel, make one rotation. How much distance it will travel? 2 pi r distance, right? So if your width of your tire is too big, this much, then how much will be area he is traveling by one revolution? 2 pi r into width of the tire. Okay. So let's see. I have the other file that we can see that how we can solve this this problem. Then it will be very clear. Okay. So let me share one more screen with you. Second, right over here. Okay, did you see the MathCAD file with some equation?
Yes, sir.
Okay, good. So this problem I put it right over here, and here is the example. This outer one is cylinder, and the red color is showing the shaft. Shaft is rotating with RPM N1. So easily you can figure out the radius of the shaft and radius of the cylinder because diameter is given. So you get the value of the gap. That means distance y. It will be RC minus RS, right? So let's see how we'll solve the problem. At first you read the problem, then you figure out what data is given. So it's a cylinder shaft 95 millimeter diameter. So I write down given diameter of the shaft ds equal to 95 millimeter. Rotating at a speed 50 rpm. So rotational speed of the shaft n1 equal to 50 rpm, right over here. Then is rotating inside the cylinder of 96.4 millimeter diameter. So diameter of the cylinder equal to right over here. Okay, and torque required to rotate the shaft is 1 Newton meter. So I say torque required to drive the shaft equal to 1 Newton meter. Then length of the shaft and the cylinder is same, is given right over here, 0.5 meter long, both shaft and the cylinder. So L equal to 50 meter. Now from there, I figure out the 1 second. I figure out the gap. After first you figure out the radius RS of the shaft, radius of the cylinder. Here is the value. I figure out in terms of meter. All you need to convert in meter. Then what need to figure out? You need to figure out viscosity of the oil. Mu equal to how much? Okay. Now what is our equation or law? We'll apply this law, right? Newton law of viscosity. That tau equal to mu del u by del y. And we know that del u by del y equal to u by y. Instead, I should put bigger u, right? And tau equal to f by a. So you put everything in this equation. Instead of tau, I put f by a, mu, and u by y. And from there, you figure out the mu from this equation. So mu equal to f by a, y by u. Now y value, we already have it, y value. We don't have the value of a, we don't have value of the f, but torque is given. We know that torque T, torque, on second, I put the wrong button. We can say torque T equal to F into R, right? So torque is given. Easily you can figure out the F, that F equal to T divided by R, okay? And we need to figure out this U. U mean linear velocity of the shaft. RPM is given, so you figure out angular velocity of the shaft, omega equal to 2 pi n1 divided by 60. So unit is coming in terms of radian per second. This is the omega. You have the omega, then you need to figure out the linear velocity, because linear velocity U equal to omega into R. So I say omega into R. So that means omega into RS, radius of the shaft, right? So omega we already found, RS we already know. In this software, he automatically read the data from the previous line. Okay, so that's why by you write down the omega into, put the radius of the value, then you get the value of U. Similarly, how will get the force F? So T torque equal to force into radius. From here you will get the force. This much is force. Now what you need to figure out? Area and also y distance. So y equal to RC minus RS. In terms of meter, you get the value of y. Now, how will get the area of the shaft? I already told you this one is rotating like that. So what does it mean? If I cut the shaft longitudinal direction with a knife and make it straight, that means this plate is moving. So this distance is 2 pi r and this distance is L. So outer surface area will be 2 pi r into L. So it's a surface area of the shaft 2 pi rs into L. L value we already know. RS we value know. So AS equal to this mass value. Now we hook up everything in the previous equation. That means this equation, you get mu equal to this one. Kg per meter second. This software giving this unit, but he don't know that unit of viscosity is Newton second per meter square. But this one and this one is the same thing. I show it over here. You say meter square, then Newton equal to how much? Kg meter second square. This is the Newton. You put second over here. Then you simplified the unit, you get this one. So I can say kg by second meter equal to Newton second meter square. So that's why I put over here. So this is the value of mu. Okay. So this software is very interesting. For example, how much the torque 1 meter, right? You sense the data. Say I am putting torque equal to 10 Newton meter. Then what will be the viscosity of the fluid? You see, it will automatically change the data. You see, result is changing. So, what is the beauty of this problem of this software? Say you are joining in a company, they make journalware, and initially they're giving a data, and you design it or you make the calculation. But after 3 weeks, your manager or your project engineer, he's saying, no, we need to change the data. What? The torque will be 15 Newton per meter. Then you don't have to calculate again. Just you change the data in the software and automatically you will get the result. Say I am going back to 1 Newton meter and my data is automatically changed again. Any data you can change. You can change length of the shaft. You can change the diameter of the shaft. The data will be automatically updated. Say I am saying the 2 meter, make it extremely long. Then you see our value is changing. Okay. So any question from this problem? No?
Sir,
Anyone?
one question. In
What to
this
say?
we have considered the surface area of the shaft. Why
Yeah.
we did consider the cross section area of the shaft?
Cross section is not moving. Which surface touches the fluid? Outer surface or the cross section?
Surface,
Outer surface, right? So you have to take the outer surface. Do you use bike? You see, we use the suspension in the bike, that one cylinder moving up and down between another on shaft, moving another cylinder, right? So in that case, which one is touching? What is the fluid? You see nothing fluid is there. Actually fluid is there. Tell me, which fluid is inside? In bike suspension, hydraulic suspension, it beginning is the air is there. It is a pneumatic one. Okay. So a shaft is rotating. Say this my hand is the cylinder, inside the cylinder. Cross section is this one. Cross section have everywhere, but it is not touching the fluid. It's rotating inside the cylinder. So this face is touching the fluid. That's why you have to take the outer surface area of the shaft. Okay, clear?
yes, sir. Yeah.
Okay, good. So let's go back to our initial problem. Do you see the screen? Problem 2?
Yes, sir.
Okay. Next slide. We'll learn about Newtonian fluid and non-Newtonian fluid. What is the Newtonian fluid and non-Newtonian fluid? Newtonian fluid, that means the fluid which follow the Newton law of viscosity. What is Newton law of viscosity? We just knew just few minute ago that tau equal to mu du by dy. If a fluid follow this law, then the fluid is called Newtonian fluid. If it does not flow, then it is called non-Newtonian fluid. And what is the Newtonian fluid? You see water, air, oil, glycerin. They are the example of Newtonian fluid. But non-Newtonian fluid, they have like also it's called Bingham fluid, like paint, ketchup, then blood. Those are non-Newtonian fluid. Then other one also non-Newtonian fluid is called piezo-plastic fluid, like styling gel. Sometimes you use gel in the styling the hair. That is non-Newtonian fluid. Other thing is called dilatant fluid. That also non-Newtonian fluid, like we use in four-wheel or a two-wheel driven car use the gear oil, that oil does not follow the Newton law of viscosity. Okay. So what is the behavior of Newtonian and non-Newtonian fluid? If you look this graph, okay, other thing, there is a other type of fluid. By name we call real fluid and ideal fluid. What is the ideal fluid? Ideal fluid, that mean it don't offer any resistance. That mean is already always flow. Their viscosity of that fluid is 0. So ideal fluid is saying no viscosity of the fluid in viscid, that is called ideal fluid and incompressible. If fluid is incompressible and has no viscosity, then fluid will call is ideal. But in reality, you will not get any ideal fluid because nothing is 100% pure. So all the fluid at least has some value of viscosity. But ideal fluid mean no viscosity. So, but when we derive some equation, then we might consider fluid is ideal. Why? For simplification. Okay. And what is the real fluid? The fluid which have the viscosity or offer resistance to flow, that is called real fluid. Now, we show you the example of Newtonian, non-Newtonian fluid and how their behavior in terms of Newton law of viscosity. So in Newton law of viscosity, if I write down again, then I have this equation that tau equal to mu du by dy. So you see, if I think tau is the y-axis, I can say tau equal to mu is the m, some constant. I'm saying m, and this is my x-axis. So y equal to mx. What is that line? Passing through the center, origin, right? Y equal to mx. So if I make a graph along vertical axis is tau, and horizontal axis this du by dy, then this line, the line passing through the origin, will represent the Newtonian fluid. So this graph is for Newtonian fluid. And dilatant fluid, this also passing through the origin, but line is not straight line. They are following some, making the graph curve, okay, not the straight line. Then you see pseudo-plastic, they also passing through the origin, but line is not the straight line, is also making some curve. Then there is a plastic, and this one is a Buckingham fluid. Now, how you can express all this line with a single equation? All those line we can represent by this equation. Tau equal to a plus b into del u by del y to the power n. So what will be for the Newtonian fluid? For Newtonian fluid, value of a will be 0. What will be the value of n? N will be 1. What will be the value of b? B equal to mu. So then this equation come down like that, right? Tau equal to mu del u divided by del y. Okay. So for dilatant fluid is not intersecting y-axis, right? How this equation how is coming? Y equal to mx plus c, but m has some power. This equation will be actually y equal to m to the power some power. I'm sorry, x to the power some power plus c, y equal to mx plus c. That means this power, if you're talking about the Newtonian fluid, this power will be 1. And this c value, intersection of y-axis will be 0. But if you're talking about the plastic, then intersection will be right over some here. What does it mean? even velocity is 0, they have some shear force. So for plastic, equation will be this one, tau equal to A plus B, and you see this equation is straight line. So for plastic, equation will be tau equal to A plus B, then the value of n will be 1. Okay. Or if I write down for plastic, this will be tau. There will be intersection of y-axis, this value. They're saying this is A plus mu del u by del y, because this is straight line. Similarly, it will be for Buckingham same, but for these two fluid, dilatant and piezoelectric, there will be some power of dy by dx. Okay. So in the exam, sometime we put the question, derive the Newton law of viscosity. Then I show the two example of problem. This type problem might come in the exam. Sometime we put question, what is Newtonian law, Newtonian and non-Newtonian fluid. Give example. Show the behavior of Newtonian and non-Newtonian fluid in a graph. Okay. Or describe the property of Newtonian and non-Newtonian fluid. Then you need to explain this graph and explain what is Newtonian and what is non-Newtonian fluid. Okay. Right over here, you see I put some series equation. What is that series equation? It's called Fourier series. So what is that Fourier series actually? You need to know. Fourier series mean right over here. This is the Fourier series. That means if you have a certain value, for example, if I write down the equation, say y equal to 4x to the power cube plus 2 into x square plus 3. So this equation I can say, instead of y, I can say f of x equal to this much. That means this line, if I'm not able to copy, I think. Let's see. Okay, this one. So from here, I can figure out f of 2 equal to how much? You just put the value over there. X equal to 2, you get some value. Say you got, just for example, you got 38 or 36.99. And what will be the value of f into 2.2? Then you might say, I'll just put that value over there, right? Yes, you can figure out. But without this value putting in the equation, you can figure out this value by Taylor series. So what is the how Taylor series work? Say you have a graph, y-axis, this is x-axis. Now if you along vertical axis is y, and along this direction horizontal axis is x. If you plot this line, it might be a graph. So when x equal to 2, what will the value of y? You already got, right? This value is you know. If you know this value, then by using Taylor series, anywhere you can figure out the value. And you see, when you use direct putting this value, that you putting x equal to 2.22, you might not get the accurate result, because this is not complete straight line. The function is not the linear. So in that case, what we'll do, over here x equal to 2. So what will be the value of that function if x equal to x plus delta x. That means final x equal to initial x. What is my initial x? Is 2 plus del h or only h. What is my h? This small value, this small distance. So instead that for this example, the small value is, I say h, this h will be 0.2. This is the Taylor series, that if you have a value at a certain distance, you can easily figure out the value of a function in a small step. Say, for example, you need to figure out the value right over here. Say this is x equal to 6. Okay, now what will do? You directly put h value equal to 4, you will get the wrong result. What need to do? Your initial value is 2 and final value you need to figure out at x equal to 6. So 2 minus 6 equal to 4. This 4 you divided by 10 or 20 or 100, so you will get the 0.4 if I divided by 10, right? So this h value you just figure out right over here by increasing 0.4, then you are getting value over here, then increasing again 0.4 and 0.4. Gradually you move to the this location, then you get the actual value. I think this kind of numerical analysis, you already know it from the mathematics. You already heard this name, like Taylor series. So that means if you know the value at f equal to x, then you can figure out the value of a function at f equal to x plus h. Okay, how? Then f of x plus h equal to f of x plus derivative of the fx into h divided by factorial 1. We take out the factorial 1, right? Next term, f of second derivative divided by factorial 2 divided by into h square. So BT of this series is going long way, but BT is that if h value you take very small, then h square will be more or less, right? So all the higher order term like h cube, h4, h5, you can neglect. And most of the time I have seen that all the derivation, if you take only the first two terms of the series, Fourier series, Taylor series, it works better. Only this much value will take. For example, you know that rho density of a fluid is rho at a distance x. So I'm saying at distance x, density equal to rho. So what will be the density? Little bit far distance from x. What is the distance? X plus del x. And what will be the my rho now? I don't know. But I can figure out by Taylor series. How? I know that I know density at a distance rho, x equal to rho. So you say fx, function fx, that means at a distance x, my density is rho. So I can put rho plus f prime. What is mean f prime? You make derivative of the function. That means I can say d rho divided by dx. So d rho by dx, this is my derivative into what he's saying h. What is my h now over here? This del x into I'll say del x. So this way we have a function, value of function at a certain point. We can figure out the value near to the point. So for example, rho, I know rho at point x is rho. So what will be the rho at x plus dx by 2? So just look to the equation at fx equal to rho. That means at this point is rho. So I putting rho. Then f prime x, first derivative of rho. So d rho by dx. Then into h. What is my h? Dx by 2. So I put dx by 2. Similarly, second derivative. So del square rho by del x square factorial 1 by 2. Then h square. What is h square? Dx by 2 whole square. Now this dx is very small value. So if square it, it will be more smaller value. So for simplification purpose, we can ignore this term. Then our value is coming only this one. Then from there you can derive some equation, or you can derive some formula. So in the next class, we will derive a formula, this one, okay? And right over here, I just give you example that how Taylor series you can figure out. Say you have fx equal to sine x. You can figure out sine pi by 2 equal to how much? 1, right? Then you increase little bit by h. That will be the value if is this much. Then you can figure out the with the Taylor series, and you can figure out with the calculator. You'll see they're giving you the same results. Okay. So far, any question